Hello and welcome to the lab makeup for Unit 7, the Combined Gas Law Lab. Purpose box reads, to observe a reaction between two reactants, sodium bicarbonate and hydrochloric acid, to produce substances that are safe to handle such as sodium chloride, water, and carbon dioxide gas. The carbon dioxide, CO2, produced is the focus of this lab experiment, and the volume of the gas produced in the reaction will be calculated using the Combined Gas Law and standard values of temperature, pressure, and volume. For any chemical reaction that produces a gas stoichiometry can be used to investigate the outcome of the reaction by measuring the volume of the gas. The conditions affecting the volume the gas occupies, if known, can be used to calculate the difference between theoretical volume and the actual volume of the gas. The ambient conditions, the combined gas law, and stoichiometry are all that are needed to investigate the outcome of the reaction. The background paragraph reads, in today's activity, using water displacement and the capture of an evolved gas, you will make use of the combined gas law and calculate the theoretical volume of gas expected against the actual volume of gas produced. From this data, you will then calculate a percent error between the two volumes of gas. While doing this activity, look for possible design errors to explain any differences between these numbers. Mr. Records will be assisting me here in the lab itself. What we have is the mass of the baking soda, the NaHCO3 pre-measured at 0.7 grams. We also have the hydrochloric acid pre-measured in the graduated cylinder, 12 milliliters the procedure calls for. We have here set up in this basin that's halfway filled with water, this graduated cylinder that was also completely filled with water and inverted into the basin of water, therefore trapping the water into the graduated cylinder with no air inside the graduated cylinder. And then the water displacement, the gas that's produced gets into this graduated cylinder, pushes out the water, and we're able to measure the amount of gas produced in milliliters. So then we take our baggie, and we're going to need to get the reactants in each of the separate corners of the bag, making sure that those reactants don't mix until the designated procedural step. Using the speaker here to facilitate the separation of those reactants. So that was the 0.7 grams of the NaHCO3. On the second side of your lab sheet, the first line of the data table, mass of baking soda in grams, you want to record 0.7 grams in that spot. We actually also have the room temperature measured. Record 23 degrees Celsius in the second line of the data table. The room pressure in millimeters of mercury is 762 millimeters of mercury. The only thing that's left for the data table is the volume of the gas collected. We won't get that to near the end of the lab. What we have to do is make sure that there's a way for the gas to get through from the baggie that has produced it into the graduated cylinder. And the tubing, the steps described in this procedure here are going to be steps 8, 9, and 10 to connect the tubing here and to get it in there. Go ahead and hold that, Mr. Records. So the beakers are there to kind of keep the reactants themselves separate from one another. So I got to coil this rubber band up, get it through the tubing, and then the ends of the baggie have to be placed through the rubber band opening as well. Let that end go. Definitely the trickiest part of this lab was this step. Pull it like from this end.
Let's get it to come down.
Now that rubber band, after that effort, of course, has sealed the baggie around the tubing inside there. Of course, we've got to make sure that these reactants aren't mixing, but we have to get all the air out of the baggie without allowing the actual reactants to mix.
Let's get one more.
One more wrap.
Yeah.
Making sure that this is secure.
We don't want to have any way for any of the gas to get out, any other way except through the tube. And that should do it.
So as the procedure says, the style like a toothpaste, you need to get all of that gas out of the baggie and through the tubing. You could do that. Making sure that, of course, none of the gas gets trapped between the tubing and the plastic bag itself. At this point, we're ready to put the end of the tubing up into the graduated cylinder, making sure not to break the surface of the water. A few inches in there. And at this point, we're ready to allow the reactants to mix. Dropping the HCl corner into the baking soda corner. The reaction resulting in bubbling, as we could see there. So allow about 5 minutes or so, 4 or 5 minutes to go by, to allow those reactants to mix together thoroughly and for the reaction to proceed. That brings that video to 12.5 minutes. In part, we can talk about the various calculations that you're tasked with completing. Number one has you come up with the equation for the actual reaction. Camera angle not working too well, so I'll just hold it like that. But coming up with the balanced equation, noting that the paragraph 1 in the purpose box gave you the 2 reactants and also gave you the 3 products. So then, making sure that the 2 are the reactants and they go on the left side, and the 3 that are products go on the right side. And then checking to make sure that the equation is balanced and going through the balancing process. Number 2 asks you to calculate the number of moles of baking soda. And it also says to include 2 non-zero numbers in your answer. Making use of a calculator will help here. The starting mass of baking soda is given on that first line. We use 0.7 grams of the baking soda that you have written there in the data table on that first line. Now it's that 0.7 grams that you need to use as your starting value, multiplying by that molar mass, with of course the molar mass value being in the denominator or bottom spot. So calculate the molar mass of the NaHCO3 and then do the division that results. In number 3, you're tasked with converting the Celsius temperature that we got as 23 degrees Celsius into Kelvin. Remember, your note-taking guide stated that you did need to add that particular numerical value to that Celsius temperature to get Kelvin. Look that value up in your note guide if necessary. Number 4, in that one there, you are calculating the number of moles of carbon dioxide. It also gives a hint there that you're to use the answer from number 2 and a mole ratio. With the balanced equation from number 1, you're going to use that mole ratio that relates the amount of moles of carbon dioxide to the amount of moles of NaHCO3 and calculate the moles of CO2 that results. In number 5, you're to use that answer from number 4 as it says, noting that we have STP conditions is the assumption in the problem. That means you're able to use 1 mole equals 22.4 liters, or simply 22 liters as indicated in the note-taking guide. And that'll give you your volume in liters. Number 6, that one has you calculate, utilizing the combined gas law, the volume that we anticipate getting in the baggie based on the room's conditions of temperature and pressure and the amount of moles of carbon dioxide that were actually formed. Noting that P1 and T1 are standard temperature and pressure. For your P1, make it millimeters of mercury, the value from the note guide. For your T1, that's standard temperature. It must be the Kelvin value of standard temperature. So then you'll put that for your P1 and your T1. Your V1, it's stating here that that's the molar volume gotten or obtained by the calculations leading up to and including number 5. In other words, your answer for number 5 is your V1. So you put all those numbers together. For your 2 values, you're looking to solve for V2. And it says at the beginning, P2 and T2 are the classroom data. And those are, of course, in the data table right up above. Make sure that you use that Kelvin temperature, and keeping the units to match for pressure, millimeters of mercury, would be good to use there. Of course, we have just a little bit more time for the baggie and the reaction there. It's nearly 5 minutes gone by. But in number 7, you want to calculate from the actual volume received that we'll be measuring here in just a couple of minutes' time. You're going to convert that into milliliters using that equivalent statement there that leads to that conversion fraction that you need. Remember, cancel out milliliters. And then finally in number 8, that percent yield, you're going to take your value in liters divided by the answer from number 6 in liters as well, and then take that division, multiply by 100, and you get your percent. So at this time it's been 5 minutes. What we're going to look at doing next is getting that baggie and the gas in the baggie squeezed through, and we should notice that we get bubbles of carbon dioxide gas going through the bag and through the tubing and into the graduated cylinder. And we'll see where we end up here.
Just hold the end of it.
Alright. Does that look like all of it?
Looks like it. Yeah.
Mm-hmm.
Mm-hmm.
Right. So pulling out the tubing while not letting the graduated cylinder break the surface, we have our volume of gas reading kind of from an upside down position. It says to measure to the nearest tens place, and that would put us at 60 milliliters. 60 milliliters of carbon dioxide gas measuring to the tens place. So then that value to be recorded as that last value in the small data table up above. Following through with the calculations, completing the conclusion, paying careful attention to the percent yield that you obtained from step number 8. Good luck.